So we are going to start talking about our next cycle here, which is measurement. And today's date is 10/21. So, when we talk about this stuff, you're going to discover that measurement is something that we are always doing. For example, the other day, I went to the grocery store and I had to pick up some bananas. And I saw that they had a sale that was going on. It was 79 cents per banana, or I'm sorry, per pound of banana. And I looked at it for a second and I said, how can I figure out how much a cluster of bananas weighs? And so I was like, well, how do I do that? So what should I do? Annie, what should I do?
Well, there's a scale there.
Yeah, that little thing that hangs down that everybody wants to put their hand in to see how much that their hand weighs, and you look up and you try to push down a little bit harder to see how much you can get it to sit there and go. Yeah, that thing. And so if I am able to measure out how much the cluster of bananas is, and I know that it costs 79 cents, how am I going to calculate out how much that my bananas are going to cost? Josh?
Well, plus tax. You don't really know how much tax.
Well, I'm not worried about the tax. I was just wondering how much it is for the bananas.
Oh, well, if you want to get more pounds, the higher the price is going to be, so.
Well, it's 79 cents per pound, and I have a cluster of bananas in my hand, and I want to figure out how much that these right here cost me.
You could go on your phone and weigh.
Well, we said there's a scale that's right next to me.
What is it there?
Well, we said there was, so that's kind of irrelevant. Yeah?
Well, it depends how many pounds they weigh. If it weighs 3 pounds, then it's,
What should I do with the bananas that are in my hand?
put them in the scale.
Okay, I'm going to put them in the scale, all right? And I see how much that it weighs, and so now that I know how much it weighs, how do I figure out how much my bananas are going to be? Connor?
If it's like 2 pounds, then you do like 2 times 7, how much?
It was 79 cents.
79 cents.
So it would be 0.79 times however much my poundage is of bananas. Very good. So that's an example of where I had to use measurement. And so measurement is used, and there's hardly a day that goes by that we don't use measurement. Okay? It's used almost every single day of your lives, and it's important to understand. All right, so we're going to take a look at it. Now, sometimes things are super big. Sometimes things are small in terms of different sizes and amounts of things. The other night, I was looking up into the sky. It was a clear night, and I saw all the stars that were out there. And I started to wonder how many stars there actually are up there. And so I started to count 1, 2, and I was out there for a while until all of a sudden I got to like the number 500 million. And I stopped and I said, well, I'm tired, I should probably go in. And I didn't get through counting all of the stars. And what happens is sometimes when we start to have really big numbers, it can get confusing. And so what we do is we use something that is called scientific notation. Okay? So I'm going to first give you the definition, and then we'll go through what scientific notation is. scientific notation is a way of expressing a value as the product of a number between 1 and 10 and a power of 10. Okay, so that's a big fancy definition. We'll go through it and break it down to make it simpler. Yep. Yeah. Yep, we're going to go through that so I can break it down for you to make it easier. Go ahead.
You have no brains today?
I know. Alright, so we have this number, 500 million, and there's a lot of zeros that are after it. Alright, and so we don't want to have to write this number out every single time that we're talking about really big numbers. So what we do is we turn this into an easier way to express it. And so it says that it is written as a value as the product of a number between 1 and 10. Alright, so is this 500 between 1 and 10?
No.
No. Okay, so we can't start there. How about here? Is that between 1 and 10?
No.
No. How about here?
Yeah.
Alright, so what we do is we begin by putting the 5, because it's a whole number, we put a period or a decimal. Okay, it's our decimal. And we put 1 0 right after it. And it says that it's the product as a power of 10. Now, as we go throughout the year, we are going to see that there are going to be numbers that are written above and there are going to be numbers that are written below. Alright, so for example, you don't need to write this part down, but later this year we are going to talk about numbers that are below. We call this a subscript. In chemistry, we refer to things as a subscript when it's written below. Right now, we're talking about powers. Okay, and in math, I'm sure you've talked about this. So if I go 2 to the second power, what is this telling me that I need to do? Yes?
2 times 2.
Okay, yes, it's 2 times 2, which equals out to be 4. Alright, what if I went like this? I went 2 to the third power. What is that telling me? Yep. 2 times 2 times 2. So 2 times 2 is 4 times 2 is 8. Okay, don't just go 2 times 3 and get 6. Alright, so your answer would be 8 in that scenario. So what we're doing is we're working with these powers. Okay, so we're going to be working with the powers. So we put a 10 because it's a product and a power of 10. And now all we have to do is we have to figure out how many places there are to the right from 5. So 1, 2, 3, 4, 5, 6, 7, 8. Now, when we express that, we put it as to the power of 8. And what that's telling us then is that we need to move 8 spots to the right from where we're at. So if we take this 5.0 and we're going to move it 8 places to the right, we go 1, 2, 3, 4, 5, 6, 7, 8. Fill in the zeros. Okay, commas go in. does this number match this number up here? Yeah. All right, and so this is an easier way of expressing our numbers of 500 million by saying 5.0 times 10 to the 8th power. All right? Let's do another example together. Let's say that I went to get a lottery ticket and I won. I won the lottery. And I ended up with $640 million. Okay? And I want to express this in scientific notation. Okay? How am I going to start to do this problem? How am I going to start to do this problem to get it turned into scientific notation? Yeah.
You start by like circling the numbers like from 1 through 5?
Yeah.
Or 1 through 10?
Yeah, 1 through 10. So I know I'm not going to start all the way out here. I'm not going to even start here. We know that the number has to be which one? Which is the first number that fits between 1 and 10? Yeah.
The 6.
The 6, because it's right here, and it's the one that's closest over here. So we express it 6.4 times 10 to, so if our decimal is right here, we have to get 1, 2, 3, 4, 5, 6, 7, 8. All right, that's how many spots that I have to go over. But we're expressing the zeros after it. So how many zeros are after it? Yes.
8.
So 1, 2, 3, 4, 5, 6, 7. All right. So let's check. So let's make it to the 7th power. So let's check our work. So 6.4, and we have to go over 7 spots. It says 1, 2, 3, 4, 5, 6, 7. Fill in our zeros. 1, 2, 3, 4, 5, 6. Commas. Uh-oh. Did we do that correctly? No. So it isn't just zeros that we're accounting for. We're accounting for place values. So if we're moving from here over 1, 2, 3, 4, 5, 6, 7, 8, this should be to the 8th power. Now if you move it over one more, you are now expressing the number correctly. So this is the scientific notation, 6.4 times 10 to the 8th power. Well, let's do one more together. I run a race in, let's go 70 to, let's go 720,000 seconds that it takes me to run a race. In your notebook, express that in scientific notation. Wherever you're writing down your notes, express it in scientific notation. Yeah. You ready? Okay, go ahead, Jack. Express it to us.
7 and 2 times.
Oh, yeah. Point. Two. I gotcha. Yep.
And 3 times 10 to the 4th power.
Okay, to the 4th, you said? All right, let's check Jack's work. So 7.2. 1, 2, 3, 4. Does that number match this number?
No.
Nope. So what do you gotta do, Jack?
You need to do 10 to the 5th power.
Let's check it now. So 1, 2, 3, 4, 5. Check it now. Does it match? So it's not just zeros, it's actually place values that we're moving over. So we gotta go from here, 1, 2, 3, 4, 5. So it becomes, how many spots are you moving the decimal to the right? Alright, so correct answer would be 7.2 times 10 to the 5th power. So we're moving from left to right, and this is a positive power. That'll make sense what that means in a second. Now, let's say that I was interested in seeing how fast a cheetah can run 10 yards. And let's say the number is, let's go 0.03, let's make it bigger, let's go, or smaller I should say, 0.008. Make it like this. Alright, so let's express this one this time in scientific notation. First thing that should stand out to you is this number smaller than the one that we had up here? Yeah, it's considerably smaller. Alright, and you'll notice that now the decimal is in front of where our first number that fits between 1 and 10 is. So what's the number that fits between 1 and 10? Yep. Alright, so 8, so 8.0 times 10 to the, now to get to that spot we have to go 1, 2, 3, 4, 5 to the 5th, but this time we were going from the right to the left, and so this time it gets a negative because we're working with smaller numbers. So anytime that you're working with small numbers, it's going to be negative. When you're working with big numbers, it's going to be positive. Alright, let's do another example of this. Let's do 0.00000075. Okay, do that one in your notebook. Lila, I'm going to give you the honors of doing this one. So what is the number that should be written first? What is the whole number between 1 and 10? What's that? Okay, 7.5, okay, because 75 wouldn't fit into that range, times, what did you put down, Lila? What's that? 8th power. All right, let's check Lila's work. 1, 2, 3, 4, 5, 6. Okay, so does that work? Yep.
I got negative 6.
All right. So, yep, negative because of the fact that it's a small number. All right, good. And so this would be the correct answer, 1, 2, 3, 4, 5, 6. And we're working with smaller numbers, so it would be negative 6. Okay, you see where you got that? Yeah.
How come you don't do the 5 too?
Do the 5 because 75,
Oh.
where's our definition? back up here, we said that it is the value of the product of the numbers between 1 and 10. And so when you're working with that, then 75 wouldn't fit into that range. Okay? Yes?
Like, how do you know when you're using the first one that you see?
Yeah, because we're working from here, the decimal is, so we'd be working this way. If you're working with the bigger numbers, like up here, we're working to make the number bigger. So it's either going smaller or bigger. Okay? All right. Then, that's scientific notation. We use it to make things easier for us. Okay? And the more that you get used to doing this, it gets easier and so on. Now, we're going to go through a couple of important vocab words. Length, for example, is something that you are already familiar with. And length, by definition, is the distance between two straight lines. Okay, so if we're talking about point A to point B, the distance that's between those is going to be the length. All right, so that's the length. We use a ruler, or we could use a meter stick as a couple of examples for how we are going to measure length. Now, when we use that, we use things like kilometers, meters, centimeters, millimeters as our measurements. So this is kilometers, this is meters, this is centimeters, and this is millimeters. Okay? By the way, why are we not using things like inches or miles, any of those type of things? Yep.
They're not metric.
Yeah, they're not metric. So you want to make sure that when you're measuring things that you are using the metric system. Okay, so make sure that you're using the metric system. Okay. Next term is mass. Mass is the amount of matter in an object, and matter is anything that has mass and
Alan Maurer and Matt Beamer
takes
report to the office.
up space. Okay, so basically anything that has matter in it is going to be mass. And in order to measure that, we need to use things like a digital scale, or we used a triple beam balance for it. And when we were measuring these, we were using grams. Okay, so the way that we measure mass is based on how much an object has of matter in it. Yep.
What's a digital scale?
A digital scale is where you don't have to futz with having to try to move the riders. You just set it on there, and it tells you how much it weighs. Yep, really easy to read. All right, next term is volume. Volume is the amount of space an object takes up. Now, when we were doing the lab, we discovered that you could measure a lot of objects using beaker and a graduated cylinder. But there's two ways to work with an object. For example, this piece of wood has a regular shape to it. How does it have a regular shape to it? Yep.
It's just a square.
Okay, yeah, it's a square or a rectangle. This side and this side are equal to each other. This side and this side are equal to each other, right? So whenever we have a regular shape, we are going to use the formula of volume equals length times width times height. Okay? And most likely you're going to use a ruler or you're going to use a meter stick to measure this. So oftentimes it's going to be in centimeters or millimeters. But because there's 3 units to it, 1, 2, 3, and we're counting for 3 sides, it's cubed. So oftentimes it could be like centimeters cubed or millimeters cubed, because there's actually 3 sides that we're accounting for. We're accounting for the length, the width, and the height. So what happens if we screw up and we put the width where the length is and the height where the length should be, and you mix them up? Is that going to make a difference in calculating our answer? No, it's not. Yeah, because it's good to learn how to make sure you know what the length and the width and the height is, but if you accidentally put them in the wrong order with multiplication, it isn't going to goof you up where you're not going to be able to get the correct answer. When does it make a difference when we have the wrong order of thing? Which order of operation? Yeah. Division and one other one. Yep. Subtraction. Then you have to make sure that you have them in the correct order. Alright, so regular shape, we use the formula of length, width, and height. So for this one, I would measure the length, the width, and the height. Okay, all of those can be done. Now, if it's an irregular shape, we are going to use something that you've already been using, which now gets a fancy name called the water displacement method. Okay, that gets a big fancy name, water displacement method. And really all that's doing is you had, bless you, a graduated cylinder or you had a beaker. You put the object in there and you use this formula. The new volume subtracted from the, that's a subtracted sign, the original volume, which is going to give you the volume change. And a lot of times we're using milliliters for these, and so your answer would be in milliliters. Okay, so if we have a regular shape, length times width times height, but in the lab, all of our objects were irregular. Yes, you could have shaped the clay into a regular shape, that would have been fine, but we just treated it as though it was an irregular one. The wooden stick was irregular, and so was the crayon. So that's why we use the water displacement method for all of those. We're almost done. The last definition is density. And density is the amount of mass per the amount of volume. which can also be written as density equals mass divided by volume, or sometimes you'll see it written as D equals M divided by V. Okay, they all mean the same thing. This is just a shorthand way to express it, D equals M over V. Now really what this is saying is that if you have, by calculating this out, say that you have a density that equals D equals, let's say, 1.2 grams per milliliter. What it's saying is that for every 1 milliliter, there is 1.2 grams that are found inside of there. Okay, so we could figure out how many grams it takes to displace the water up a certain amount. Okay, so if we wanted to know that we have 3 milliliters, and I wanted to know how much mass is inside of there, I could take this and multiply it by 3 and get 3.6 grams per milliliter, and that's how much mass there would be in 3 milliliters of water. All right? Yes?
I have a question. I thought we used multiplication of mass times volume.
It's mass divided by volume. Yeah. And so this is telling us that information. There's also a rule of thumb that if it is 1.0 or greater, it is going to sink in water. If it is 1.0 or less, it is going to float. Okay, so if this number is above 1.0, it is going to sink. If it is less than that, it is going to float per 1 milliliter of water. It said that if it's 1.0 grams per 1 milliliter, it will basically stay floating. But if it's anything greater than 1.0, it is going to sink. All right? So you should have been able to look at your work and decide, okay, the crayon went in. Was it greater than a hole as 1.0? If yes, it should have sunk. The wood stick, if it was greater than 1.0, it should have sank. If not, it should have floated. And that's it for notes.